Alrighty. So, as I've said many times, don't let gravity get you down or drag you down. Yeah. No, I can't get the slideshow started. What is going on with this computer? No, the more buttons I press, the worse it gets. Okay, here we go. So, gravity was invented in 1665. It was all discovered?
It kind of been invented.
I'm teasing, of course, right? So it was actually, you've heard of the Black Death, the bubonic plague, which ravaged Europe and the United Kingdom in the 1600s. Monty Python made a whole movie about it. They shut down university and Newton had to go home. Okay? Yeah. So he had to go home, and of course he was one of those guys that didn't stop thinking, and he started thinking about gravity. Now the story goes he was sitting under an apple tree and an apple hit him on the head. That's quite likely, scholars believe, probably not true, but he may have actually seen an apple fall, saw the moon. You know those days you can see the moon during the day, right? And got thinking, the apple falls, the moon appears to fall. I wonder if it's the same thing. And of course, it is. Now, about a century before him, a gentleman by the name of Johann Kepler had developed laws to explain the motion of the planets, but didn't know why the planets moved. Newton was the one that wondered if the same force caused an apple to fall to the ground from a tree, and of course, he was right about that. So this led him to what we know as the law of universal gravitation. Sounds ominous, right? I almost want to use my James Earl Jones voice to say it. Between every two objects, there exists a force of attraction, as I mentioned many weeks ago, I think, right? Every two objects, there exists a force of attraction. This force is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Sounds like something Sheldon might say in walking down the street, right? What does this mean? The force is proportional to the product of their masses. It means that the bigger the objects, the greater the force. It's a direct relationship, and it's the product of their masses. So if one gets bigger, like if one doubles, the force is double. If the other one also doubles, well then the force is now 4 times as much. Double times double. But it's inversely proportional to the square of the distance between their centers. In other words, the farther they are apart, the less the force. In fact, twice as far would actually mean 4 times as less force. Newton, fortunately, was able to put that into a formula. It looks like this. F equals big G m1 m2 all over r squared. What does the F stand for? Force. I'll leave the big G for the time being. What does the m1 stand for? Mass 1. m2 obviously is mass 2. And the r, what do you think the r stands for? Sometimes written as d. Yeah, it's distance, right? In this case, they use the r because it's a circular kind of thing, and so the r is the distance between the two objects, and you'll notice that it's square. What do you think big G is for? You're close. Is it 9.8, Joey, do you think?
No.
No. Why did you say it like that? Are you scared of what?
Getting it wrong.
It's okay if you're wrong. I'm wrong every day. Is G 9.8 everywhere in the universe?
Depends on the mass.
Does it? Like on Earth, isn't G 9.8? Like more or less 9.8 everywhere, right? What about on the moon? What's it on the moon?
0.
Is it 0?
1, 2.
1.6 actually. Okay? So in fact, big G is what we call Oh yeah, there's the diagram that goes with it, right? So M1 is the mass of 1, and M2 is the mass of 2, and this Fg is the force between them, the mutual force, the one that, like the moon and the earth that we were talking about the other day. And then the R is the radius between the centers. But I still haven't really explained what big G is, have I? Okay? Fortunately enough, you will not be responsible for this formula. It is not on the Rampton flowchart. I will not give you any problems using it. However, when you get to grade 12, you will have to. And I will tell you that, where is it? Oh, I don't tell you what big G is? Really? Big G is what we call the universal gravitational constant. And if my memory serves me correctly, it's 6.67 times 10 to the minus 31. Something you don't need to worry about. He had a really good calculator.
He was like an abacus.
Actually, that's something that you're going to look into, is how they actually come up with, like, if we were to determine the gravitational force between Joey and Jake, how would we do it? Yeah, and there is, you can actually come up with that number. It's not easy to do in a high school lab. Okay, so now a little bit of sort of definition here. The region around a mass in which a second mass will experience a gravitational force is described as a gravitational field. The region around the Earth, right, that a second mass will experience a gravitational force is described as the Earth's gravitational field. If I take Zach's Pepsi from KFC, empty cup, and I drop it, or I let go, the Earth's gravitational field pulls it down. The cup is in the gravitational field, right? Is the moon in the Earth's gravitational field? Sure is. It's just a little farther away. Is it falling towards the Earth?
No.
Yes, it is. I know, it is kind of scary, Joey. How come we don't need to worry about it?
Because it takes a while. The Earth's falling too.
Neither of those is true. If let's just say that Zach's KFC cup was full of delicious Pepsi, and Zach sat, come here, come sit on the chair for a sec, Zach. We'll pretend here a little, it'll be fun. Okay? And Keelan, you come on over here and just sort of stand on the other side of it. Okay. Now, if I were to take the cup, can you pitch it for him? So if I were to drop it, he would get delicious Pepsi all over his head. Do you mind? That's empty, right?
Drop it, guys.
Okay. He would get Pepsi all over his head, see? Right? Now, if it were full, we should fill it up with water. Right? If I toss, wait, just step back a little bit. If I toss it over him, is it in free fall?
Yes.
Absolutely it is. How come he doesn't get wet?
The water falls away.
The cup's doing what?
Free falling.
It was free falling like this too.
It's in a parabola.
Okay, you're on the right track there, because it's also doing what?
Horizontal.
Moving horizontally. What's the moon doing?
Horizontal.
Moving horizontally. So it's falling towards the Earth, like the cup towards Zach's head. Your head is like the Earth, right? The cup is falling towards it, but it's also doing what? Traveling like this. Now, the problem is on Earth, when I do this, right? Eventually, Keelan has to catch it, right? But if you were indeed the Earth, right, and the moon does this, what would happen when it gets to here?
Just keep going.
You've got a gravitational field, and you've got this cup stuck in your gravitational field. That's what's happening. Jake.
I heard that we're losing the moon by like an inch every year.
Yeah, it does tend to, the orbit is, yeah. You won't have to worry about that. You'll be long dead. Okay, thanks, guys. Okay, so this was actually on the outline here. I got to hustle so we can go see that little experiment. The strength of the field at any place is defined as the gravitational force that a unit mass would experience if placed there. So we would say, like on Earth, right, the gravitational force is 9.8 newtons. And so we would say the gravitational field strength of the Earth is 9.8 newtons per kilogram. That's all that really means. That's all that really means. Okay? The strength of the Earth's gravitational field is 9.8 newtons per kilogram. That's all it means. This strength is represented by a small g. When a gravitational field is drawn, and you will be required to know this, the field lines are closer together where it is strong, and where it is weaker, they are further apart, much like this. Okay, there is a rather simple diagram of the Earth's magnetic field. Where the lines are closer together, gravitational. Right here, they're close together. The Earth's gravitational field is strong. Up here, where the lines are farther apart, the gravitational field strength is weaker. The closer the lines are together, the greater the field strength. Those are not vectors. These black ones that I drew, they are not vectors. They are what we call field lines. They look very much like vectors. They point in the direction that the field is experiencing or producing, but it's not the length of them that matters, it's the distance between them. Okay, and more on that in a bit. This diagram implies that gravity is weaker as you climb in altitude. We tend to know that, right? As you go farther out away from Earth, it gets less and less. Now, a graph of gravity at different altitudes would appear somewhat like this. Like as you go up in altitude, what happens to the gravity? Goes down. Goes down. Does it ever go down to zero? Like, could you go far enough away to get the Earth's gravitational field to go to basically zero?
Yes, probably.
You could. How far away would it be, Joy?
17 times the distance of the moon.
Exactly. 17 times the distance to the moon. Space shuttle astronauts do not orbit 17 times the distance of the moon. Right? You'll notice that at an altitude of about 400 right here, gravity still pulls at about 9.5 newtons per kilogram. That's about how high the space shuttle is orbiting, 400 kilometers up. Space shuttle astronauts are experiencing a gravitational force of about 9.5 newtons per kilogram. But I thought they were weightless. Are they weightless? They are free falling. Okay? They just never land. Much like the cup that was free falling over Zach's head. I mean, it did land. Chris, why do I keep calling you Chris? Keelan eventually caught it. Come on in, Curtis.
That's just what Gillespie said. If you want to come watch the egg bungee jump thing in the air,
We got to come now?
if you want to, it doesn't matter.